So welcome to Finite Elements. I have the honor to invite Daniel Mueller, who is going to give us a lecture series. It will be a question and answer as well. So in the middle of this presentation, I'll also ask you questions to see how you've been, through all your experiences. I know you've gone through a lot of different companies now. So he has a bachelor's degree. One of the best engineers I met across, really big picture thinker. That's why I really like, and I invited you back, is because of your way of thinking of the problem in a different way. Another thing is I see a lot of engineers make excuses. When there's a problem, they make an excuse. Oh, I don't know how to solve that. Oh, I can't do this. I can't do that. The attitude that Dan brings is a very different one. It's like, there's a problem. Let's figure out how to compromise or come up with a solution that works. Always looking for that solution. Master's degree from University of Southern California. That's where I think you were there. The Boeing company, a lot of experience there with the DARPA Alaska program. In fact, I thought I was connected to you somehow peripherally. At SpaceX, he did have a lot of influence. Again, we'll be careful about what we say because it's recorded. So again, everything he will talk about is very top level, but we had a lot of intersection there. Really enjoyed collaborating with you. And then you went and I think it went before COVID. Very interesting hearing how that went. But you work with electric airplanes, I think is what you told me, which is kind of cool. I never, I'm pretty sure you were dealing with batteries and stuff like that. Yeah. That'll be very interesting to know how that's going. And now he's working at Relativity Space, where he's a manager for upper stage structures and mechanisms. And he has a tremendous amount of personal interest. And yeah, just excited to have you here and seeing you once again. So, thank you. So with that, I'll pass it to you. I'll be near you to ask questions.
Okay.
Go ahead.
Well, yeah, I'd like to keep this just like informal. Also, anybody can ask me questions. How much time do we have? When do I need to be done?
You can go.
Okay. All right.
I'll stop you. You have
Okay.
20, you have half an hour.
I have half an hour. Okay. So yeah, Vinay introduced my professional background. Like more philosophically, what did my career look like? I started out in aerospace. So I'm an aerospace engineer. Started out as a stress analyst. So I was doing finite element analysis 100% full time. And more importantly, spent the majority of my time as a full-time stress analyst doing hand calcs. So it wasn't like I was sitting and running Abacus and Patran and whatever millions of tools there. I don't even know what they have now. But I was mostly running hand calcs and using FEA to check my work. So just like before I get into the details and like some of this philosophical stuff, I'm a big believer in just being able to understand what's going on before you jump into tools. And yeah, I've moved from being a stress analyst through a lot of different roles. We could talk about that if anybody's interested at the end, to now running a team of engineers, designing flight hardware, using this stuff to actually get launch vehicle design, reusable launch vehicle design. So I'm like very intimate with all these principles that I'm going to talk about. So I wanted to just touch on 4 general topics of like practical finite element analysis and specifically in aerospace engineering. So yeah, not everything's testable. Margins are low, mass is critical. There's not infinite time. All models are wrong, but they have to be useful. And then the last one is, I guess, tangentially related to finite element analysis, but a building block approach can save you a lot of money, a lot of time, in some cases is really your only option to make sure something's going to work. So yeah, not everything's testable. Specifically, not all flight hardware is testable. So just like running a quick thought experiment, if testing was incredibly cheap and fast, would we still use finite element analysis? I mean, it's a useful thing to think about because there's so many different cases. If you think about a piece of primary structure on a launch vehicle, for example, or on an aircraft wing, and think about that piece of flight hardware throughout its entire life. You have manufacturing, you have transportation, you have flight cases, you have flying in rain, flying in hail, flying in Abu Dhabi, who knows? It's almost impossible to come up with a complete test campaign that looks exactly like everything you want to prove, including factors of safety and everything else that your regulators want to see in a test. Even if it was incredibly cheap and fast, it's almost impossible. It's also generally true that physics always wins, and we can't always impose the right test like you fly conditions. So what do I mean by test like you fly? On the ground, you're not able to replicate every single thing that happens in flight. You have a test fixture that your hardware is attached to that is different than what you're flying to. You're not always able to apply hundreds of degrees to your flight hardware under load. So this is inherently a limitation that everyone faces. Am I good? And then there's just practical considerations of like, what are all of the things that happen to a piece of flight hardware in reality? I mean, if you just look at these ones that I listed, it's almost impossible to come up with one test which can capture all of those. And even if you consider doing multiple units of testing, it's still basically, in my opinion, impossible. So there's strategies you can use to get around that, but you need FEA and structural analysis methods and tools to cover that. I touched on the third one already, that there's a significant number of possible conditions for flight hardware, especially primary structure. And then, yeah, the reality is in aerospace, we don't always have the luxury of going and just supplying a worst case on worst case on worst case. We would never be able to fly anything useful for anyone. So we generally have to do a lot of load cases, a lot of optimization work to be able to get something in the air. Yeah, and then FEA gives you this really useful ability to take 1 million load cases and bake that into maybe 10 load cases that you can do on the ground and actually test something to make sure that it's going to work. So this is how things work in reality. We generally follow these principles to get something flying safely.
Let me ask you this question. So early, when you don't have the infrastructure to do testing, and say a lot of folks may go into startup, for example, where there's probably no testing equipment, and you have to come up with an initial design concept. Can you tell us a little bit about how Finite Elements can help you through that process and what kind of uncertainties you have to consider?
Yeah, so let's imagine we're in a rocket startup. So we have a launch vehicle we want to fly. We have some customers that we want to put on top of this rocket, and we're early days. So you're like the very first structural designer at this company. You're a designer and you're also an analyst, and FEA is one of your tools in your toolbox. You'll end up getting a bunch of very conservative loads from the loads engineer that sits right next to you that you go and assess. And in general, you have to have a conversation with this loads engineer and understand what this product is all about and consider what the right amount of uncertainty is to hold early in a program versus late in a program. So if you're just pencil and paper, back of a napkin, drawing a rocket and doing some sizing with FEA, you're going to hold super high uncertainty on all of that. And then late in the game, when you're ready to go test something, when you actually built this qualification test stand, for example, your uncertainty is going to go down quite a bit. But generally, I see it going that way.
And are there ways to reduce uncertainty over time using testing or something?
Yeah, I don't remember if I include that in this talk, but grounding your finite element models in reality is super important. So generally you go into, let's say, a really expensive qualification testing. You know, if you imagine a wing test, right? And it takes a lot of effort to go build a wing for an aircraft and test it. You're going to want to make sure that that thing's not going to break in this qualification test. And it might actually be the case that you've built a whole production system around this single qual test working. So it's very important that that works. You use the outcome from that test, so strain gauges or deflections or a million other things you could do with load cells, for example, to ground that model. And then you can use that model to buy back conservatism that you might have been holding elsewhere. So because this model is now grounded to tests, you know that you can go look at other cases that you didn't test and feel confident about that working, or design a new vehicle which has a very similar piece of hardware that has it's been grounded.
And one final question. In your experience, is it common to have components on an aircraft or launch vehicle where maybe doing testing is just too much extra effort, so may as well just analyze it with a higher factor of safety?
Yeah.
Is there a way to do that?
Yeah, definitely. So we use this a lot in launch vehicle structures. So Yeah, we have different factors of safety depending on whether you go test something or whether you are doing what we call, has a few different names, no test, qual by analysis. We hold higher factors of safety on that qual by analysis approach, but we generally limit those structures to things which are pretty easy to analyze. So, if we had, let's say, a thrust chamber assembly in an engine, we're not going to be able to use no test on that because it's very complicated. There's a lot of things you need to understand in reality. But if it's a bracket holding a tube, we think we understand the loads pretty well. It's really only seeing some loads due to vibration. So we tend to use this no test approach for that. It's pretty common. Yeah. That also requires your models to be good though. So you can take this approach and have crappy models and then like it's not actually doing anything. It's not adding any value. Cool. Yeah. Yeah, so following not everything's testable. If we, as I mentioned, if we had huge mass margins, we would just overcompensate with more material and make the part heavier and de-risk failure. But generally we can't do this. And then even if we could, with really high mass margins, reality typically throws a lot of things in your direction, like lack of money, lack of time, especially schedules and cost always get in the way of actually making these things feasible. So FEA is generally the most economical way to do things to make sure that the flight hardware is working. Obviously, a really big exception here is flight hardware that requires super complicated analyses where it's difficult to ground models. My thrust chamber assembly is a decent one, though I would argue we kind of know how to do that. But I've worked on a few different designs. I don't know if anybody's familiar with the Falcon launch vehicle, the like grid fin structure. That's extremely difficult. You have really weird aerodynamic loading, very high temperature gradients, not a great way, or rather we didn't have a good way to get flight data back. So there's some scenarios where you want to kind of tailor your risk posture and make sure you have the right approach, or you just decide to go test something to reduce risk. Questions on this one?
Yeah, I mean these are great points because there are a lot of parts in launch vehicle design or reentry. Take a reentry vehicle.
Yeah.
Reentry vehicle like a capsule coming back from space, right? Like one of those, like the Dragon capsule, or one of those.
Mm-hmm.
The temperature conditions are very complex, and to test something like that on the ground is almost impossible. Because how are you going to apply heat that's so high across the whole surface for a long time on the ground? We can do some of that with Limo tests and RJet tests at the Ames facility, but at a smaller scale. And so there are cases where, like what you said, where there's a lot of complexity.
Yeah.
I agree with that.
Before I keep going, any questions at all on anything? Yeah.
So in aerodynamics, it's common to make scaled down models.
Yeah.
To test stuff. Is it possible to do the same thing with structural problems?
So repeat the question so they can hear.
Yeah, let me say that question again. The question was if you can use scaled down models like they do in aerodynamics to I think to like ensure that the structure is going to work. It depends. So generally, in order to get a useful result out of let me rephrase this. It depends what you're looking for. So it depends what you're seeking as an output. If you have a very, let's say, nonlinear phenomenon in your structure that you need to understand, it could be that a subscale model is going to represent that very well. But let's say that I wanted to test something to ensure that it's going to work in flight. Let's say that I had a tube-shaped structure that was connecting two stages of a launch vehicle. I couldn't test this in compression and say that that's something that's this size in compression and prove that that's going to work at the full scale, unless it was made identically. It had all the exact same types of manufacturing processes. It had the exact same material conditions and everything. It's generally very hard to get things to shrink down to a small scale to work. There's a lot of exceptions. A good example would be if you have a really long tank, for example, on a launch vehicle, you could test a shorter tank and then use a qual by similarity approach. So you could try and hit equivalent margins of safety on your subscale article to then demonstrate that the full scale article is qualified. So it kind of depends what your objective is, but yeah, you can do it. Any other questions?
And I think you're gonna talk about the building block approach, no?
Yeah. Yeah. So FEA is generally a useful thing in aerospace, no matter what you do.
Sure.
As a design engineer, you can just work a lot faster. As a stress engineer, it's your job. If you're a programmer or product lead, you're going to use this to de-risk flight hardware that your team's designing. So like when I'm working with my team, I'll generally be asking for finite element analysis models to de-risk like possible failure modes that I think are going to cause us problems in the future or to optimize. And then as a systems engineer, this is crucial for your compliance deliverables. So it might eliminate some testing you need for compliance later down the road. Yeah, and then there's some pretty cool things you can do with FEA, which I don't see used very often in my industry, like boots on the ground, except for R&D maybe. These are three pretty key ones. The second one is quite common. So vehicle level dynamics models. I don't know if you've talked about coupled loads analysis or anything like that, if that's a topic here, Vinay.
So was it?
You talk about CLA at all in this class? Or any
No,
dynamics? Okay.
no, but we did cover dynamics
Okay.
and we did just covered mass, mass matrices and
Yeah,
stiffness
okay.
matrices. But you can take a minute to explain it. I
Yeah,
think they'll
so
enjoy that.
yeah, so vehicle level dynamics models means we have an aircraft and you take that entire aircraft and you simplify it into a dynamics model that you can use to predict loads. So you can use these dynamics models to basically simulate flight and what happens in flight. And that's like a version of simplifying load cases like I talked about earlier. So that's a very useful tool. That's, I would say it's I guess a niche area, but it's super important.
Let me relate it to something we discussed
Sure.
in class. So remember, guys, when we discussed that if you run a very large model that's millions of degrees of freedom, it will take forever to run. Remember that? So when he talks about simplified dynamic models, he's talking exactly about what we covered, I believe, last week, which is you can take the main modes of the system, remember the main modes, and just come up with how much amplitude participates in each of those modes. And that simplifies it from millions of degrees of freedom to just a couple of amplitudes they need to get that get multiplied by these mode shapes, because every motion can be made up from those mode shapes times corresponding amplitudes, right? So that's what the simplified thing means.
Yeah, it's actually usually impossible to actually build a vehicle and make really big, complicated models. We just, due to time reasons, always have to simplify things. And that takes a lot of engineering judgment that goes beyond just using tools. So coupled loads analysis, or if you're in my industry, you might hear CLA is quite common. And then optimization for layouts. There's some really cool structural sizing tools around, which are great at this. OptiStruct is one. There's a few other that do something similar, where basically you design a structure and then it'll tell you like what size if I have a stiffened structure, it'll tell me what thicknesses my skin needs to be and height of my stringers needs to be. It's really powerful stuff. It's things which actually make you a lot faster. And then my last one's a favorite, exploratory analysis. If you're just not sure what the hell's going on with something, or you're curious about how something's working, making a simple model to tell you in which direction to be looking is actually pretty useful. I don't see that one done very often, but I do it myself quite a bit. Okay. Yeah, this is really important. All models are wrong, but they have to be useful. So it's kind of like thinking if it's more like if we wouldn't bother with FEA unless it provided some kind of measure performance benefit. So this all comes down to grounding your models and making sure that you've had adequate peer review. So I think Vinay was talking about this as I walked in. I generally don't believe models unless they've had someone review them. It's just you stare at this thing for hours and hours and you miss things. So have your buddy sitting next to you take a look at it, or have your manager review with you and talk about how to make things a bit more like open and transparent when you're building them. This also causes a lot of major problems. I've seen a lot of models which haven't been peer reviewed, even by very smart people. And typically these are people who have a lot of confidence and don't want their models to be reviewed, have major mistakes, and that causes like sometimes millions of dollars of rework that we have to do. So it's actually at all levels, it's important. And then, yeah, make sure you do testing in your models, even if you've gotten a peer reviewed and you think that it's right. Make sure that in the end, before your stuff flies, if it's critical enough, that your models are grounded.
What is the most common error that you've seen? I'll give you mine after you're done.
In building models,
Yeah, models, heat transfer or finite elements or whatever.
yeah, I mean, in structural analysis, bad assumptions.
Yeah, sure.
I don't like bad assumptions. Like I thought that this dome structure was 300 thou, but it's actually 100 thou
Sure.
because they forgot to ask the person who owned the dome. It's generally little things like this.
Mhm.
And then that propagates, 6 months down the line, and all of a sudden it's like, oh, huge disconnect.
I'll give you mine. My top two. My top two in no order will be unit problems. So units are wrong or inconsistent. Because the software has no units, doesn't tell you what units you're using. So you're kind of on your own to figure that out. And the second one is, like say you're modeling a geometry or something like that. The drawing says that is a certain radii and whatnot. So you put the exact same thing as in the drawing, but in the manufacturing floor, they're making something else. So meaning whoever designed it said that the radii is going to be 30 mil or whatever. And the manufacturing floor is saying, well, we'll try our best. I don't think that's feasible, but they do whatever.
Mhm.
And so I see a discrepancy between what's in the model and what's in the manufacturing floor.
Yeah. I don't know, it's a mistake or what I would call it, but I also see a lot of models which are way too detailed. That someone spent like weeks and weeks working on, which could have been done in like a day with a hand calc or something.
And it doesn't even run.
Yeah, it's like, oh, this is different material. Okay, let me run the model. It's gonna take 3 days. Like, yeah. It's like kind of, yeah. What's up?
We haven't really talked about like, I guess how you guys tackle, like making accurate models for like additive.
Oh yeah. Yeah, definitely.
Be careful not to.
Yeah, all good. Additives tough in general because have you talked at all about composites?
None in this course.
So things get really interesting when you have process sensitive materials. So I actually consider things like additive technology to be very similar conceptually to things like composites. And we'll talk about the building block approach at the end. But additive means, yeah, you have this really cool ability to build a part in any direction. You release a lot of constraints that you have in subtractive manufacturing, but it means that every part that you make actually is kind of a special snowflake, and it has its own unique ways of having defects that you have to consider. And this is actually the same in composite flight hardware. You have a structure, a bespoke structure, which you go build and took a lot of time to invest in like tooling and whatnot. And you get something which is not the same as if a different vendor was going to make it. If a different vendor was going to make it, it's definitely just a different part. So we tend to follow this building block approach, like I'm going to talk about next, with things like additive and composites. In terms of modeling, I wouldn't say there's anything very uniquely different, but it's how you assess different failure modes that's really key. Did that answer your question?
Yeah.
Okay, yeah. So generally rules to follow in your finite element analysis models. Always be distrustful of your own results, especially if they look good. I can't tell you how many times I've made something which I thought was good and just move forward with it, just to have it like go back and look at it 2 weeks later and it's completely wrong. So hand calcs, peer review, sensitivity of analysis is also a pretty useful technique there. Follow a checklist or make your own. Versus your system 2. So it's like your fast versus slow method of thinking, really like slow down and try and be deliberate about the steps you're following. I'll talk about the building block in a second. And then, yeah, the last point we've touched on several times already. Okay. Have you guys talked at all about the building block? approach?
This course it's not like the ones
Okay.
I developed for you before.
Got it. Okay. So this building block pyramid looks really boring and not very interesting, but it's like one of the most important concepts in developing reliable flight structures. It's very simple. So at the top, you have, let's say, you could consider this for analysis methods. You could also consider this for flight hardware. So this is showing you analysis methods, but at the top, we can consider like cutting edge, very advanced, explicit, whatever, multi-physics analyses. But at the top of this pyramid, you could also put like your whole aircraft. Like your whole aircraft lives at the top of this pyramid, and that you want to prove that this aircraft is going to work. And the way that you do that is not by going and attacking that whole problem all at once. You break it down into different levels. So at the bottom of this, you have like really, if we go to the analysis portion of this, which is what is shown, you have basically hand calcs and handbook style analyses. And to be honest, you can get by with this to prove out the flight vehicle structure in a lot of cases. There's definitely corner cases, and like some of the new technology, like a capsule is a good example, might need some of that, but we made it to the moon with basically that and like the second layer maybe. So it's really not necessary to go do super fancy things. But it does make you a lot faster. So it's a balance, and it's more about thinking about what the best approach is. On the hardware side, in terms of testing, this looks like coupon testing, like taking a section of your, wing skin and pulling on it, and taking a fastener and pulling on it until it fails, and developing, we call material allowables. So you'd have material allowables at your lower level. You take these little building blocks of material allowables, you build that into a stiffened panel structure that you analyze with a more complicated FEM. You prove that that panel structure is going to work. And then you might take one whole, let's say, wing section in your complex FEM. You make a pretty complicated model of this wing that includes a section that you'd already tested. And then you're going into that full scale test with already a pretty good understanding of how this section works in a reasonably complex model that you've already validated all the way up. You go do that, it works, and then yeah, that's one big part of your aircraft that you've qualified. So this is just a really convenient way to break down really complicated analysis and test problems that we find ourselves dealing with all the time. You could take this approach with literally any piece of structure on an aircraft or a launch vehicle, basically.
What happens if I go straight to large scale testing of an aircraft with no modeling? So we've seen failures. You can read them in the New Seattle Times, where the Boeing 787, 777,
Yeah.
Airbus A380, all of them had wing failures at the root of the fuselage. I don't know how familiar you've seen
Oh,
those,
yeah.
right? Don't you think the building block could have been one of the things that could be missing there?
Yeah, for sure. It's all about risk. Like if you're willing to risk a test program failing, you want to go into tests and just see what happens. And if it fails, great, fine, whatever. But like that's pretty expensive and not really helpful in the end. So you might get lucky, but you might also do a whatever $10 million test of an aircraft wing and have no idea what the outcome was. Oh, I applied some load. Well, what was the build condition? What load did you see at the root of this aircraft wing? So I mean, the way that this could have been avoided is by building, having each one of these building blocks. We talk about maybe a fitting at the root of this wing that broke. You look at the bolt, you look at the lug section, you look at all the different material properties that go into it. You do some testing at the subscale. Then you build a model of the wing and you look at what the loads at the root are. You take a little subsection of that root section, test it, and then go into your full scale wing test, knowing what the loads are, knowing what the allowables are of that fitting, and you go just prove that it's going to work at the full scale, but you've kind of already got the story closed.
What happens if during a test, say like when they had the Columbia accident, they had like foam shooting out and they didn't know why? What happens if like something unexpected like that happens during a test.
Hmm.
So,
And
so
like,
hold on, that was not a test, that was a real thing.
but like they had it happen on like previous flights.
Yeah.
And what happens if like something unexpected happens and you go back to the model and you like can't find?
Hmm. Yeah. So now we're talking about,
So repeat it.
yeah, so the question was, what if something unexpected happens in a test or in flight? Now we're talking about a failure or accident I forget what the official terminology is.
A mishap
Thank
investigation.
you. That's what it is. Yeah, mishap investigation. So this becomes a different thing. Let's imagine we had our aircraft wing test, the exact one we were talking about, and something broke in that test. If your model was predicting that nothing was going to happen, your model is wrong. Because physics always wins. That was one of my points. So it's not that physics was wrong, your model was wrong. And it might actually not be that your model's wrong, it might be that they built something wrong, or it might be that they built the wrong thing, or it might be that what you thought you were testing was just a totally different thing than what you were analyzing, so your model's wrong. So you have to take failures as like real learning experiences. They happen. That's actually kind of, one would argue, the point of doing testing. It's much worse for something like that incident to happen in a real flight. That's really unfortunate. So yeah, did that answer your question?
And I want to add to this, when often failures happen, it's something that was identified previously. It's just somebody felt that the risk could be accepted. And it could be due to prior pressure, it could be due to cost considerations or other. 737 MAX is an example of that, right? The determination was done, we can keep flying, and then a second aircraft goes down, and that's when the program shuts down and they have to redesign. So a lot of times it's very difficult to make decisions that balance the risk with what we want the best for the population. And that's not an easy balance to walk, right? I don't fully blame them because it's not an easy balance to manage.
That was my last slide. What questions do you all have? We can talk about career stuff or whatever technical topics, all whatever. Yeah.
What was the process like getting a job internationally?
Oh, that was an interesting one. So
So what was the process? The question is, what was the process for getting a job internationally?
so how I ended up there was I knew someone at Boeing who ended up in Munich working for this electric aircraft company. And I thought it would be fun to live in Munich for a few years, which was one of the main reasons I took that job. It was a really cool experience. Getting the job, actually, there's a lot of companies in Europe now, engineering companies specifically, who are trying to hire English speaking candidates, and they make it pretty easy. You got to get a visa. You've got to be kind of far from, depending on whether it's good or bad from your family in the US. So yeah, it was not so bad. It was a good experience. I'd highly recommend it.
Kind of the same note, like, if I'm an international student, so I can like do aerospace stuff in the US. Is there any other place that you would recommend going, like looking into? Like,
Any other countries?
So let's take that question after class, that one specifically. I have my reasons.
Okay.
You don't mind?
Hey, what's up?
Similar vein to that, like how did you decide it was time to jump between like a different company? Were you
Oh.
like, interested in the new area of engineering?
So the question is what motivated him to,
Yeah, which like,
when you're motivated to switch companies and what made you do that?
Yeah. Yeah, that's a good question. So I've been, I'd say, pretty lucky because I've never, none of the projects I worked on that are listed here like failed and I never got fired. Somehow.
So you fired yourself?
Yeah.
You looked at yourself in the mirror and you said you're fired?
I mean, sometimes people just get unlucky. But so I mean that was good. The reason the jumps were just better opportunities. I think being open to new opportunities at all times is pretty important. So I wasn't particularly looking to leave SpaceX actually. It was just like a cool opportunity came along and we went for it. I went for it. My last move to relativity space, I knew a bunch of really good people who are working at relativity and they were looking for someone to help them. Small company doing something pretty ambitious. So I thought it was a good time to make a move.
Okay, let's do a lightning round quick.
Sure.
So the first word that comes to your mind,
Oh God,
the most challenging project,
Falcon Heavy,
the most easy project,
batteries,
the worst error in a finite model,
foot gapping on a heat shield.
oh man. The easiest, the most obvious mistake in a finite model.
Wrong material.
What is, it happens to me all the time. I just saw that last week.
Yeah.
Your favorite project?
Oof. Crew Dragon Falcon.
More fun, working, well, you probably don't want to tell me.
Huh?
Germany or United States?
More fun living in Germany.
Okay,
Yeah.
cool. Well, with that said, guys, let's just, if you have, your resume, if you have your resume, you want to talk to him a little bit more, let's do it outside. Your question, I have a reason why we're not tackling it right now, but we'll give you guidance, don't worry about it. All right, thank you, guys.
Thank
If
you.
you don't mind sticking around for a little more.
Yeah, of course.